welcome to MeduHub. Today we are going to talk about nucleophilic substitution reactions in alkyl halides and their stereochemistry. So in alkyl halides, let's say Rx, the halide group leaves and in a nucleophilic substitution reaction, a nucleophile, which is an electron-rich species, replaces it here. In alkyl halides, nucleophilic substitution reactions are of two types, SN1 and Sn2 reactions. SN1 reactions are called substitution nucleophilic unimolecular. Uni means one. And SN1 reaction is a two-stage process. Two-stage process where the first step is the alkyl halide ionizes to give a cation, and the leaving group, that is the halide, it leaves as X minus. This is the slow step and this is the rate determining step. And the second step is the fast step where the nucleophile attacks the carbocation and we get the final product. In SN2 mechanism, this is called substitution nucleophilic bimolecular. Bi means two. Bimolecular. In an SN2 mechanism, this is a one-stage process where the nucleophile directly attacks the substrate and forms a transition state where the carbon is attached to 5 bonds simultaneously. What happens in this transition state? The bond between the carbon and the halide starts to weaken and the bond between the incoming nucleophile and the carbon starts to be formed, and we get the product, which is this. Let us discuss these, taking an example now. So we'll start with SN1 first. Let us take an example of an SN1 reaction. We have this compound. In the first step, what will happen? This will ionize in the slow step to give a carbocation, CH3, CH3. This is the carbocation and the bromine ion will leave. Let's say it is reacting with the nucleophile, which is OH minus. Now in the second step, this OH minus will attack this carbon here and give us the tertiary alcohol as the product. CH3 OH Br minus stays as it is. So this is the product. In this reaction, this is a two-stage process. The first step is the rate determining step. In an SN1 mechanism, the concentration of the substrate determines the rate of the reaction. So it is a first order kinetics reaction where it depends only on the concentration of this substrate and does not depend on the concentration of the nucleophile. Right? Let us see another example where we see an SN2 mechanism taking place. For an SN2 mechanism, let us take this example. CH2 Br reacting with the nucleophile, let's say OH minus again. So this is a one-step process where the concentration of both of these will determine the rate of the reaction. It is a bimolecular reaction. It is a second order kinetics. So rate of the reaction will depend on the concentration of both of these. Now in this reaction, since it is proceeding via SN2 mechanism, what will happen? The nucleophile will attack this alpha carbon here. This right now has a tetrahedral geometry. What will happen here? CH3. The bond between C and Br is here. The nucleophile will attack from this side. So simultaneously in this transition state, the carbon has a covalency of 5. It is simultaneously bonded to 5 atoms. In this transition state, the bond between carbon and bromine will slowly start to break, and the bond between OH and this carbon will slowly start to form, and we get the product as this primary alcohol. So we have discussed what SN1 and Sn2 mechanisms are. The examples we had taken were not of optically active alkyl halides. because they did not have a chiral center. But what if the alkyl halide that we take is optically active? That is, there is a carbon atom which is completely asymmetric. What happens in that case? The mechanism followed is the same, but what happens to the products? Let us see. In the case of an SN1 reaction, let us take this example where this is a chiral center. There are 4 different groups attached to this carbon. This undergoes SN1 mechanism and reacts with the nucleophile, which is again, let's say, OH minus. What will happen now? In the first step, we will get a carbocation. This bromide ion will leave here, and this it stays as it is. Now this carbocation will assume, because there are 3 bonds to the carbon, so it will assume a planar geometry. So imagine that this is in the plane of the blackboard. The Br ion has left, Br minus ion has left, and now the nucleophile is free to attack this carbocation here. It can attack either from behind or it can attack from the front like this. There are 2 routes, right? So it can lead to a mixture of both plus and minus isomers. Now what happens when this carbocation is sufficiently stable, it is sufficiently long-lived, and it has a low reactivity, and the concentration of this nucleophile is also low, then there will be enough time for the bromide ion to leave, and OH minus will have a lot of space around this to attack from both the sides, and this will give to an equimolar mixture of both the plus and the minus isomers. This is called racemization. So racemization, or a 50-50 ratio, is obtained only when this carbocation is sufficiently long-lived, it is stable, and the nucleophile is present in a low concentration. What happens in actual ionization? This bromide ion is somewhere in the vicinity, right? So to some extent, it prevents, there are repulsions between this OH group and Br minus, and it prevents the attack from the backside. In that case, we still get 2 products. One is this, which is the retention product, and the other is this one, which is the inversion product. But because of the presence of this Br minus in the vicinity behind the molecule, the attack was somewhat hindered from the back. The retention product is formed in less percentage compared to the inversion product, 60 or 40. In some cases it is 30 or 70 also. So though in an SN1 reaction with optically active halide, we get a racemic mixture, but the inversion product is sometimes more in yield than the retention product. So we get like a unequal racemic mixture. So we understood how in an SN1 mechanism, the products are a racemic mixture when an optically active alkyl halide is used. Let us see what happens when we have an SN2 mechanism. We'll take the same example. Bromide is here, this hydrogen is here, and CH3 is here. This is also a 2-degree alkyl halide. Now what happens in an SN2 mechanism, the nucleophile OH minus attacks the substrate directly here, right? Now in this step, the 3 groups already attached to the carbon, initially the 4 groups were in a tetrahedral geometry, right? But when the OH minus attacks, these 3 groups which are already attached, C2H5, CH3 and hydrogen, will assume a planar geometry. So we can write them like this: C2H5, CH3 and hydrogen. So these 3 will be now in the plane of the board. This bromine was behind and the OH will attack from the front, right? So this transition state is somewhat a planar geometry with Br and OH in a collinear line but perpendicular to the plane. We can draw it like this also. So the Br bond, the C-Br bond is breaking and CH3H, and the bond between OH and C is forming in this stage. So what happens when the OH approaches this molecule, these three bonds will start to move and compress in the direction where the Br minus is leaving. So all of these groups will start to move in a direction and compress to make space for OH. Right? Br leaves, these three groups keep on moving, and this leads to an inversion in the configuration. Inversion. So that in case of an SN2 mechanism, we get an inverted product. We can draw it like this. So in case of an SN2 reaction, we get an inverted product. In case of the SN1 reaction, we get a racemic mixture. So let us summarize what we learned today. We discussed SN1 and SN2 mechanisms. SN1 is a unimolecular mechanism, which is a two-stage process. Where the first step is the rate determining step, and it proceeds via a carbocation formation. Whereas SN2 mechanism is a bimolecular mechanism, which is a one-stage process, and it proceeds via a transition state where carbon has 5 bonds simultaneously. And then we talked about the stereochemistry of these two when we use an optically active alkyl halide which has a chiral carbon. So in case of SN1, we get a racemic mixture which can be equimolar, or we can get the inverted product more than the retention product. And in case of SN2, we get inversion always as the product. Okay. So this is it for today. Thank you so much for watching. I'll see you in the next video.